Hello everyone. I'm very disappointed I couldn't get to China because of a visa issue, so my apologies for that. I'm going to talk today about structure-property relationships in fluoride containing bioactive glasses with applications in dentistry. I'm Robert Hill. I'm a glass scientist who specialises in degradable glasses, and I'm the research director at the Dental Institute at Queen Mary University of London. But I would also like to say a little bit about this young lady, Xiaojing Chen. She's probably the best PhD student I've ever supervised. She probably won't tell you, but she won the prize for the best female PhD student in the UK while she was with me. She developed the first ever chlorine containing bioactive glass and filed the first patent with me and a colleague on chlorine containing glasses. And these glasses are actually now commercially available in what is termed the Vitamin C toothpaste, which is sold both in the USA and in China, and it has Federal Drug Administration approval in the US. She also developed the first ever Fluorapatite glass ceramic, and perhaps more importantly, she's just a great person and lovely to work with. Again, a little bit about my background, because this impinges on what people do. Some people say history determines the future. So way back in 1988, I was part of the materials group at the Government Chemist that won the Queen's Award for the development of glass ionomer cements, which I suspect a lot of the dentists here have actually used. But later on, I was invited to give a lecture at Imperial College, and Larry Hench, who's the grandfather of bioglasses, actually appointed me as a reader at Imperial College. And both Larry Hench and Alan Wilson were not only good scientists, but they were very much interested in translating their research in the laboratory into practical products like bioglass or glass ionomer cements. The research drivers for bioactive glass toothpastes and remineralizing fillings, which I'm going to talk about, are the following. Tooth decay is the most prevalent disease in man, and more than 90% of adults have at least one filling. In the UK, the costs to the National Health Service are more than £1 billion per annum. But perhaps the biggest problem is that tooth decay is the largest reason for hospital admissions for children under 6 years old in the UK, and this is often for full mouth extractions. The market for toothpaste is in excess of $12 billion per annum, and that of dental fillings over $2 billion per annum. And there's a pressing need to replace mercury-based amalgams, and I'm not quite sure whether China signed up to the Minamata Agreement, but I suspect it is, and the World Health Organization document. And in the EU, we have an EU directive and an EU report, all wishing to eliminate mercury from the environment and to restrict or ban amalgam-based fillings. The UK government wants to see benefits from its research spend within universities. They want to also see increased employment opportunities, improved treatments and reduced healthcare costs. And to achieve this, we at Queen Mary file quite a lot of patents, and we've also set up a university spin-out company, Biomin Technologies Limited, to help us exploit and translate the research from the laboratory to the commercial arena. And we actively exploit our science and transfer our technology to the commercial world. The area of tooth decay and dentine hypersensitivity and fillings is of general interest to the population, and we've had a lot of media articles both in newspapers and online published, and this is just one example. Most people think of glass as being chemically stable and chemically inert, and thankfully when it rains the glass windows don't dissolve. It would be disastrous if they did. But much of my research has actually been concerned with glasses that degrade or dissolve. And these include compositions that form cements for dental and medical use, like the glass ionomers, or perhaps release trace elements, like some phosphate glasses. But more recently, I've been interested in glasses that will form apatites, the tooth mineral and bone mineral, what are termed bioactive glasses. So I'm going to show here a video that Jing did during the course of her PhD. And this is us really showing off. So if we start the video now, let me just start it. On the left, we have what's labelled WG window glass, and on the right we have something labelled BG or bioglass. And Jing is now taking about 0.1 gram of bioglass, putting it into 50 mils of water. She'll do the same with the window glass, which she's doing at the moment, and then she'll shake them up. And what you'll see when she holds them up to the light is the bioglass is a clear solution. It's dissolved completely in just probably 30 or 40 seconds, whereas the window glass has formed a cloudy suspension. Now, the glass that we produced for this video actually dissolves far too quickly for any practical use. The one we actually use in the toothpaste actually takes 10 to 12 hours to dissolve. But you wouldn't want to be watching this video for 10 or 12 hours. So a bioactive glass is a glass that dissolves in the body. It releases calcium and phosphate ions, and as it does so, it increases the pH. It forms hydroxycarbonated apatite, the same mineral phase that comprises tooth enamel. It will bond directly to bone and tooth, and you can change the rate at which the glass dissolves and the level of apatite it forms by varying the chemical composition of the glass. And most compositions contain silica, calcium oxide, soda, and phosphate or P2O5. And the glasses consist largely of polymeric silicate chains. The accepted mechanism proposed by the inventor of bioglass, Larry Hench, shown in the top right there, is as follows. Sodium ions are exchanged for hydrogen ions at the glass surface. This exchange results in a localized pH increase, and this is particularly attractive for dental applications because caries and tooth decay occurs under acid conditions. This is then followed by alkaline hydrolysis of the silicon-oxygen bonds of the glass network, the formation of what we term silanols, and then the formation of a silica-rich layer. And this is then followed by migration of calcium and phosphate to the glass surface to form a calcium phosphate film, and this crystallizes to form the hydroxyapatite, or HA. And in the case of bone, this HA then it becomes incorporated with collagen fibers, which stimulates bone formation. In the mouth, The calcium phosphate and hydroxyl ions in the saliva are in quasi-dynamic equilibrium with the apatite mineral in enamel. So over on the left on this slide, we have calcium ions, we have phosphate ions, and we have hydroxyl ions. And then over on the right in red, we have the hydroxyapatite, the Ca5PO4-3OH. Under acidic conditions, the hydroxyl ion concentration is low, and that reaction actually moves away from apatite towards the ions in solution. Conversely, if we push the pH up, in other words, increase the hydroxyl ion concentration, or we increase the calcium or phosphate concentration, we will move that equilibrium over to the right in favor of apatite formation. And that's particularly attractive if you want to remineralize enamel or you want to prevent acid erosion or caries. But in dentistry, we also tend to add fluoride to things like drinking water or restorative materials. And this is because the fluoride ion can swap with the hydroxyl ion, and this pushes the equilibrium over in favor of apatite formation. But the apatite we now form is not hydroxyapatite, but fluorapatite. And the fluorapatite is much more acid stable and much more durable. And this is one of the attractive features of fluoride. It's also important to note that we can swap the calcium for strontium, and strontium also has a caries inhibitory role. In terms of the glass structure, we can actually predict how quickly a glass will dissolve by counting the number of silicon-oxygen-silicon bonds in the glass structure. And this we term the network connectivity. And the science here is perhaps a little bit heavy and complex for dentists, but essentially if we have a network connectivity close to 2, the glass will have its bioactive properties. The phosphorus content in the glass, or phosphate content, is also important. The phosphorus in the bioactive glass exists as orthophosphate, the same form that's present in the apatite. And it probably exists as a dispersed phase of about 50 nanometers contained within the silicate glass. So we may have in bioglasses the dissolution of 2 glass phases. It's important to design the glass so that when you put the phosphate in, you don't cross-link up the silicate phase of the glass and increase the network connectivity. As you increase the phosphate content of the bioactive glass, it speeds up the formation of the apatite as well as increasing the amount of apatite formed. It does reduce the pH rise slightly, and by increasing the phosphate content of the glass, you can get much faster and more apatite formed than with the original bioglass, which is known as 45S5, developed by Larry Hench. I've worked closely with a chap called Professor Matthias Eden, based in Sweden in the Arrhenius laboratory, and this is a quote I've taken from one of his papers. And he says, as long as phosphorus remains predominantly as orthophosphate and the average silicate network polymerization, which I would term network connectivity, is favorable, the bioactivity, in other words, the apatite formation, increases monotonically for increasing phosphorus content of the bioglass. So in the glasses that we produce at Queen Mary University of London and Biomin Technologies, we deliberately use a high phosphate content, about 3 times that of the Novamin or Bioglass. Now, Larry Hench and a student called Spilman actually investigated fluoride-containing bioglasses back in the late 70s. But they substituted calcium fluoride for calcium oxide or for soda. And some people are still doing this despite Delia Breuer's work. If you do this substitution, you impede or inhibit the formation of the apatite because you cross-link up the glass. And what we do is we essentially add calcium fluoride without changing the network connectivity. Larry Hench and Spilman also made the assumption that the apatite formed was still hydroxycarbonated apatite. And in actual fact, we've shown that where you've got fluoride present, you always form the fluorapatite. So this is, in the top right is Delia Breuer, who also worked with Jing, and we did 19F magic angle spinning nuclear magnetic resonance. And what she showed was the fluorine in the glass was surrounded by metal cations, where N was largely sodium and calcium. And what we then did was add fluoride to the glass rather than substituting it for calcium oxide to maintain a fixed network connectivity or structure to the bioactive glass. And this contrasts, as I said before, with Spilman and Hench, who swapped calcium fluoride for calcium oxide, which reduced the bioactivity. And small amounts of fluoride in the glass speed up the apatite formation and resulting fluorapatite being formed rather than the hydroxycarbonated apatite. And fluorapatite is much less acid soluble, and increasing the fluorine content also reduces the pH rise slightly. You have to be careful, because if you add too much fluorine to the glass, what you form is calcium fluoride or fluorite rather than the fluorapatite, the fluoride analogue of the mineral. We said earlier that if you put too much calcium fluoride into the glass, then what you form is calcium fluoride. And what this graph here shows is, as you increase the mole percent calcium fluoride in the glass, that the fluorapatite produced declines at the expense of fluoride being produced. So the two patterns we filed corresponds with the two arrows on the diagram. The first one is for low phosphate glasses, and the arrow at higher calcium fluoride contents is for higher phosphate content glasses. We can see the effects of using a low phosphate or a high phosphate glass in this data here. So these are Fourier transform infrared spectra, and as we go from A to F, we're increasing the calcium fluoride content. And you can see with the low phosphate glasses to the left, in the circled area, the peaks are weak and they disappear fairly quickly, whereas on the high phosphate bioglasses to the right, the peaks are much more intense for the PO stretching bands of apatite. So with higher phosphate contents, we form much more apatite, we also form it. So this is all the science, and I'm sure as dentists you probably weren't too interested in the science, but you're probably a lot more interested in the applications. And so we're going to look at a number of applications of these fluoride bioglasses in the dental area. So the first application is toothpastes. So both the fluoride bioactive glass and the chloride bioglass that Jing developed as part of the PhD are sold to toothpaste manufacturers and are in the Biomin F and Biomin C toothpastes. And you'll find a lot of information on these on the Biomin website, www.biomin.co.uk. The toothpastes are a lucrative market, more than $12 million per annum. And for example, you also have for sale in China this product for from GlaxoSmithKline called Sensodyne Repair and Protect. And for example, over more than 1,000 tonnes per annum of the 45S5 or Novamin glass is used in this toothpaste. Bioglass was designed and developed really as a bone substitute. It was never originally intended for use in toothpastes. Despite this, the Novamin, which is the 45S5 glass, works surprisingly well in the Sensodyne Repair and Protect product. The Biomin F glass, in contrast, that we produce and that was developed at Queen Mary, is designed and optimized specifically for use as an additive for toothpastes. It differs from the Novamin in it contains fluoride within the glass structure. It has a much higher phosphate content in the glass, and it has a smaller particle size. And all those changes are designed to improve its efficiency as a toothpaste for treating dentine hypersensitivity and for promoting remineralization. The Biomin F toothpaste is designed to treat 3 common problems: tooth decay or caries, acid erosion, which is the dissolution of the tooth surface, for example in acidic drinks in the absence of bacteria, and dentine hypersensitivity, which is tooth pain associated with cold or mechanical stimulation. The causes of dentine hypersensitivity are numerous. It can be the result of receding gums. For example, as you get older, the gums recede, exposing more of the root of the tooth. It can also be a result of loss of enamel through acid erosion or tooth decay, or a contributory cause is the wear of the enamel at the cervical margins where it's thinnest through excessive toothbrushing. And if you have dentine hypersensitivity, you don't want an abrasive toothpaste because you're likely to remove more of the enamel at the cervical margins and expose the tubules in the dentine, which cause the fluid flow and result in the pain sensation. This slide on the top right has a picture of Professor Ten Cate from ACTA in Amsterdam, and I have cut and pasted from one of his review papers where he says low concentrations of fluoride have a beneficial effect on enamel and dentine remineralization. And after fluoride treatments, salivary fluoride concentrations decrease exponentially to very low concentrations within a few hours. So we can see this in the graph on the right, where the diamonds represent the exponential decay of the fluoride in the mouth with time. And if you take typical salivary volumes and salivary flow rates, you will find that the fluoride concentration will fall below 1 ppm value, which I take as a therapeutic concentration of fluoride, within about 90 minutes. And what Ten Cate said was for treatments to be effective longer than the brushing and salivary clearance, fluoride needs to be deposited and slowly released. And this is what we designed the Biomin F glass to do. What we want is a glass that doesn't result in high fluoride concentrations, but results in a continuous release of fluoride over 10 to 12 hours, the time period between brushing your teeth. And this is the red line on the graph on the right. In order to prevent the glass particles being washed away in the same way the fluoride is washed away, we need to stick the glass particles to the tooth surface. And the polymer in the toothpaste is polyacrylic acid, which has carboxylic acid groups which chelate calcium ions in the enamel surface and also calcium ions in the glass particle surface. So the polymer serves to stick the glass particle to the tooth surface and prevent it being washed away, and then the glass particle will dissolve over 10 to 12 hours in the mouth, releasing calcium and phosphate, and in the case of the Biomin F, fluoride ions as well. The polymer in the toothpaste is the same polymer that's present in glass ionomer cements that provides the adhesion to the tooth structure. So the glass ionomer cements, of course, have polyacrylic acid in them too. The Biomin glasses are also designed so they dissolve faster when the pH is lower in the mouth. So the glass will dissolve about 10 times faster at pH 4 than it will at pH 7. And this is a very attractive, smart response of the glass, so that when you drink an acidic drink, the Biomin glass dissolves faster, increases the pH, and releases calcium, phosphate and fluoride ions to protect the tooth against acid dissolution. The particle size in the toothpaste is optimized to occlude the dentinal tubules. And if you believe Brandstrom's theory, it's fluid flow within these dentinal tubules, which are typically 1 to 5 microns in diameter, which triggers the nerves in the pulp chamber, which gives the pain sensation. The Biomin particles are quite considerably smaller than that of the Novamin particles. So the average particle size is about 14 microns for the Novamin, and it's about just under 6 microns for the Biomin F. And this means there are a lot more particles of the Biomin glass that are capable of going into the dentinal tubules and occluding them to prevent the fluid flow. There are some additional advantages of the smaller particle size. It results in a smoother texture to the toothpaste, which consumers like, and it also reduces the abrasivity of the toothpaste towards enamel during brushing, which is particularly attractive. The fact that the fluoride is not washed away means the fluoride is used much more effectively in the Biomin F toothpaste, and this enables the fluoride content of the toothpaste to be reduced, and it's typically about 1/3 of that of a typical fluoride toothpaste used in Europe. So it's about 500 ppm. The lower fluoride content reduces the risk of fluorosis. Here we show the fluoride release for different time periods, and the fluoride drops with time. It's not flat top like my ideal schematic that we had before, and this is because quite a lot of the fluoride is used in fluorapatite formation. But you can see we still have 2 ppm of fluoride at 24 hours. So here we have some X-ray diffraction patterns of the Biomin F glass after immersion in artificial saliva. And what we can see is the development of the characteristic sharp diffraction peaks for apatite, which start at about an hour. It was important for us to demonstrate in the Biomin F and the fluoride bioglasses formed apatite, and this is the crystal structure of fluorapatite. And at the centre of the crystal we have the fluoride ion that's marked there, and that is surrounded by 3 green spheres which are calcium ions. And we term this site in the fluorapatite lattice an FCA3 because it's a fluorine surrounded by 3 calciums. If we had an hydroxyl ion there, the hydroxyl ion would be displaced above the plane of the triangle, and that would result in the apatite being slightly less stable towards acids. So what we're looking for is this FCA3 site, and this has a chemical shift of -103 ppm in the NMR, and what we can see is in the original glass we've got a broad spectrum for the orange spectrum at the bottom, which is glass, and then even as short as 30 minutes you can see that a broad peak developing which becomes sharper with time and has a chemical shift of -103, which shows us that we're forming fluorapatite. Here we have the scanning electron micrographs of dentine before treatment with the toothpaste, and so that's on the extreme left, and you can see the dentinal tubules here. Let's see if we get on that. So here, for example, here's one of the dentinal tubules, here's another. And then the middle micrograph is after brushing with Biamine F toothpaste and immersion in an artificial saliva. And you can see that the tubule diameter has decreased quite markedly. And you can also see, if you look carefully, some little glass particles sticking still to the surface of the dentine. When we give it an acid challenge, which is citric acid to mimic the consumption of a sugary drink, you can see that quite a lot of this surface apatite and these little glass particles are dissolved. And some of the apatite, the fluorapatite that's dissolved, reprecipitates. So we actually look to have better tubule occlusion after the acid challenge. With the other toothpastes that form, for example, hydroxycarbonated apatite or occlude the tubules with calcium carbonate, those species disappear when given an acid challenge and the tubules reopen. So the fluorapatite gives us much better, durable tubule occlusion, particularly under acidic conditions. We believe that the fluorapatite formed with the Biamine F forms not just on the surface, but it forms preferentially on the apatite-rich walls of the peritubular dentine. And in general, crystals like to form on a bit of the same or very similar crystal phase. And so the peritubular dentine, which is extremely apatite-rich, acts as a nucleating surface for the formation of more fluorapatite. We measure the fluid flow through dentine discs before and after treatment with different toothpastes, and this slide shows a summary of the different data. So here on the extreme left we have the Biamine F, which is giving about a 90% reduction in fluid flow through the tubules of a dentine disc. The Novamin toothpaste, the Sensodyne Repair and Protect, gives quite a good performance. It's about 65%. The Colgate Pro Relief, which is the other leading brand, gives you just under 70%. And then we have some other toothpaste for comparison. A potassium nitrate one, which you wouldn't expect to occlude dentinal tubules, but contains some silica particles, for example, which do have a tubule occlusion effect. And also some nanohydroxyapatite toothpastes, which are also giving about a 50% reduction in fluid flow. We have also measured how effective the Biamine F toothpaste is in promoting remineralization. And for these studies, we take a little enamel block, which I'll show you here. So there is the enamel block, which sits in the center of a cell which contains about 2.5 mils of liquid, and we have passing through the enamel block an X-ray beam, and we measure the amount of the X-ray beam passing through the block, and from that we can determine how much mineral is present. So we start off by pumping through the cell an acid solution to demineralize the surface of the enamel. We do that for 24 hours. We then switch to an artificial saliva, and we apply the toothpaste to the enamel block every 12 hours. And we measure the rate of remineralization that occurs. And the next slide shows the data. So the block on the far right is labelled AS, which is artificial saliva. So when you immerse the enamel blocks in artificial saliva, you get a remineralization effect. The next one is Sensodyne Repair and Protect, which does about twice what artificial saliva alone does. And then we have MI Paste Plus and MI Paste, which you may know in China as Tooth Mousse and Tooth Mousse Plus, which is an amorphous calcium phosphate, which also does quite well. But then if you look at the Biomin F, it is about almost twice what the commercial products are, and about 3 times what artificial saliva is. So you can see the Biomin F has a very high remineralization rate. So the Biomin F toothpaste releases fluoride, it forms fluorapatite. The apatite formation process is very rapid. It forms the apatite preferentially on the peritubular dentine, and it exhibits a very high reduction in hydraulic conductance, and it's extremely good in terms of enamel remineralization rates. One of the things as scientists where you occasionally get sent pieces by members of the public, and this lady sent me a picture of her daughter before and after treatment with Biomin F toothpaste. And you can see she had some white spot lesions on the front 2 teeth, and they seem to have disappeared after a month's use of the Biomin F. And she was a bit critical of the dentist, because this is a 7-year-old, and the dentist said, "Oh, don't worry about it. A teeth will fall out eventually and it'll be replaced. We don't need to do anything." But she said, "Oh, she looks horrible. What can you do about it?" He said, "No, don't worry about it." But she went and used the Biomin F toothpaste and got really quite a nice result. These are the toothpaste that we sell, or various other companies around the world. So we sell, for example, a version of Biomin F and Biomin C in China. The bottom one here is Biomin C that's sold in the US. We've got the Biomin F that we sell. The one on the far left is from Dentist in Thailand, and the one top left is HiDent Pro, produced by Abbott Laboratories. We're selling it around the world. We have the patents that support the fluoride bioglasses for toothpaste, but the patents also include patents for professional dental products, and we have a strong intellectual property portfolio, and quite a lot of the patents are granted in the US. We've been operating until recently largely in the consumer products arena and toothpastes, but the core patents and technology are also useful for a wide range of other professional dental products, like, for example, orthodontic cements, restorative fillings, endodontics, adhesives, and air abrasives, for example, are all potentially good, attractive application areas and markets. So the big drive is for composites, and the existing composites are technique sensitive. You require very good moisture control. You really have to use rubber dam to get good results. You need to build up the restoration incrementally in thin layers. The bonding agents used often break down with time to couple the composite to the tooth structure. You always have gaps between the restoration and the tooth, and generally they fail as a result of bacteria permeating down these marginal gaps, resulting in secondary caries. And they are time consuming to place properly. The glasses we've patented and are using in toothpastes are high phosphate fluoride containing glasses produced by Mel Quenchroot. But when it comes to composites or putting them into resins, we use very low sodium content glasses. And we also use higher fluoride contents. And the patents are being licensed by Biomin Technologies out to other companies. We need to replace mercury-based amalgams because the reasons I cited earlier on in terms of the Minamata and EU and UN legislations and agreements. The big problem with composites, as we already alluded to, is that, which is shown on the right here, is you always end up with a gap, and bacteria permeate down that gap and they cause secondary caries or tooth decay beneath the restoration or filling. What we've been doing is replacing the inert glasses used in conventional composites with bioactive glass, and we've been adjusting the refractive index of the glass to match that of the resin so that we get some translucency in the material, which gives better aesthetics but also enables us to cure at greater depth. These new bioactive composites release calcium, phosphate and fluoride. They form fluorapatite as the toothpaste does. And more importantly, the ion exchange process at the surface, particularly in the marginal gaps, results in a pH rise. And the bacteria involved in caries like an acidic pH. So the increase in pH towards 7 discourages many of the bacteria associated with caries. But also, over time, we infill the marginal gap with crystals of fluorapatite, which tends to seal the gap and prevent bacterial infiltration. This slide shows a backscattered scanning electron micrograph of a cross-section of a bioglass composite. You can see the bioglass particles in the resin matrix here. But if you look over to the right of the dashed yellow line, what you can see is the particles have degraded. There's a change from being whiter to a darker grey, and you can see this one's reacted almost completely, whereas this one here, the centre hasn't yet reacted. And this is after the disc has been immersed in artificial saliva pH 4. So you can see the glass particles of the surface are reacting. They're not reacting all the way through. This thickness is only about half the thickness of a human hair from the dashed line to here. If you do the same experiment, but you now immerse the disc in artificial saliva at pH 7 rather than pH 4, what you can now see is this white deposit on the surface of the disc. And if you look carefully, you can see some needle-like crystals of apatite. The reacted layer in the glass surface is now much thinner. It's only about 5 to 10 microns thick. And this is the effect of pH on the glass degradation, which occurs much more rapidly at acidic pH. We're going to talk now about Atraumatic restorative therapy, or ART, and we're using ART in conjunction with a technique that we use extensively at Queen Mary called X-ray microtomography, which is a way of imaging materials and teeth in 3 dimensions at micron scale resolutions. And we're using, rather unusually, a bioactive composite filling rather than the glass ionomer cement. And at the end of the experiment, we're doing scanning electron microscopy to get some further information. So the X-ray microtomography allows us to visualize samples in 3D, and in this case we're using a resolution of about 20 microns. We build our own machines at Queen Mary, and these have what is known as time-delayed integration, which allows us to quantify the linear attenuation coefficient and determine absolute mineral concentrations. And in our custom design scanner, the detector is simultaneously moved as a sample is rotated, as shown as the next slide, which isn't there. So Atraumatic restorative therapy is developed by Joe Frenken. It's normally carried out with glass ionomer cements, and some glass ionomer cements have a slight remineralizing action. In other words, they can put back some of the lost mineral from decayed dentine. But one of the problems with glass ionomer cements is they don't release significant amounts of phosphate, which limits their remineralization potential. What we're doing here is ART with a fluoride bioactive glass composite. So here we have an X-ray microtomography slide on the far left of the carious tooth. We then hand excavate the carious lesion, which you can see in the middle, and then we fill with the bioactive glass composite, which is like good. So here we have the bioactive glass composite, and the image is at 2 weeks, but what you can see here, if you look carefully down here, can you see the marginal gap that's present? You can see, in fact, a white spot lesion here, and you can also see the carious lesion. On the right, we have the graph of the linear attenuation coefficient as a function of distance along this yellow line. And the blue is the original, and the red, the green and the pink are after 2, 4 and 6 weeks. And what you can see here is an increase in the mineral content in the carious lesion and a loss of mineral in the composite surface. And you'll also see we form this little peak here as well, which is actually apatite that forms at the interface. Now, if we just click on one, I think you can just see, we just pop back again, just watch carefully towards where the yellow arrow is. You can see the increase in the mineral content in the carious, in the hard carious dentine left after the ART procedure. Just move to the difference image. So we're subtracting the first image from the last image, and the areas that are whiter are where we've got an increase in mineral content, and the areas that are darker are the areas where we've lost mineral. So you can see we've lost mineral or from the bioglass particles in the composite surface. We've increased the mineral content in the carious lesion. You can also see a white line down here and a little bit of one here, which is apatite formed in the marginal gap, and you can also see the apatite formed here. You can also see that we've formed apatite in the bubbles that we had in the composite. We're now going to look at SEMs, look at the microstructure after we slice the tooth with a diamond saw, and we're going to show you micrographs correspond to here, here, and here. So this is in the marginal gap, and what you can see is we've got this white deposit in the marginal gap and even in the crack that runs off the marginal gap, and this is apatite forming in the marginal gaps. Now here, whoops, I've got a timer on this. Here we have the Bioglass composite in contact with sound dentine. You can see the tubular structure of the dentine running in this direction. You can see the Bioglass particles in the composite. You can see the reacted layer in the composite. And you can see that these two glass particles in the composite have partially reacted. But this, here we were getting an increase in mineralization, so what we term remineralization, but this was sound dentine. So if we've got sound dentine, it can't remineralize. But if you look carefully, have a look here. If you look carefully at the dentinal tubules, you can see a white deposit on the inside surface. And this is the apatite forming on the inside wall of the peritubular dentine like we had with the toothpaste. So this is not remineralization, this is just extra mineral forming within the dentinal tubules. This slide shows the base of the cavity, and what you can see is the dark layer in the composite surface where we've lost mineral in this backscattered image. You can see an increased mineral content at the surface of the dentine. You can still see we haven't remineralized the carious lesion completely. And this is a gap that's formed as a result of shrinkage in the SEM because of water loss. So in summary, calcium and phosphate and fluoride release can result in remineralization of carious lesions left after ARC procedures. The exchange of hydrogen ions and calcium ions results in a basic pH, particularly in water-filled marginal gaps that may inhibit acidophilic bacteria, ones involved in caries. And apatite formation can occur in marginal gaps, resulting in them infilling and potentially stopping bacterial penetration and secondary caries. We're going to look now briefly at the use of bioactive glass in an orthodontic adhesive, and we're replacing the inert glass again with a fluoride bioglass. And we have calcium and phosphate and fluoride release out to 6 months. We haven't measured it any longer than that. And we also have a pH rise. So this is the problem, the big problem in orthodontics, that after fixed bracket orthodontic treatment, the patient's often left with this white discoloration as a result of white spot lesion formation on the tooth surface. And this is because it's difficult to clean and brush around the brackets, and plaque tends to concentrate in the gaps and the crevices around the brackets, resulting in demineralization of the enamel. So what we've been doing is putting bioactive glass into these adhesives, and the top one here shows a tooth with a bracket bonded with a bioactive glass adhesive and then immersed into artificial saliva at pH 4 for 18 hours. And you can see there's no whitening of the tooth surface. And this is the difference image in the X-ray microtomography, and there's no evidence of any demineralization of the enamel surface. This is in contrast with what happens with conventional orthodontic adhesive, which was Transbond XT, and you can see whitening over the tooth surface, all over the tooth surface, which is a result of pores created in the enamel as a result of demineralization. And you can also see this as a dark line on the enamel surface in the difference image from the X-ray microtomography. So some final comments. If you understand glass structure and chemistry of apatites, this is key to the development of new bioactive glass-based products, and good science leads to good products. And if you want to find any of my papers, you will find them on the Biomin website, www.biomin.co.uk. So thank you very much for listening to me. I hope you've put up with the science part of the talk, and I hope you found it interesting. And again, congratulations to Jing on our new centre. Finally, some acknowledgements from people who've helped me, funding bodies, etc., and particularly to all the people at Queen Mary and Imperial who have helped me in these studies. Thank you.